Good evening, everyone. Welcome to the 12th and the final live session for the course Concrete Technology offered by NPTEL. I am Archit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I have conducted weekly live session for the entire course duration. So in today's session, we will have first revisit the last live session that was an extra session for the remaining part of week 11 content in a quick recap manner, and then we'll look into the things that we are covered in week 12 content. So week 12 content is all about special purpose concreting, in which we'll discuss about an overview of special purpose concrete, then different types of special purpose concrete starting from high strength concrete, ultra high performance concrete, self compacting concrete, fiber reinforced concrete, roller compacted concrete, high density and low density concrete, and finally recycled aggregate concrete. In between, I have some objective questions, around 15 to 20 questions in total, that will challenge your understanding about the concept. And finally, I'll conclude the session and I will address any other queries post discussion. So, in last session, we continued our discussion about corrosion in reinforced concrete structure, where we discussed kinetics of corrosion, which where we first discussed Butler-Volmer equation and two special cases of this equation depending upon the amount of polarization we provide. So first is when we provide very high polarization, so we get slope constant and TEFL extrapolation curves. And when we apply very small polarization, we get Stern-Gary relationship, which can be used to calculate polarization resistance if we know the corrosion current and TEFL slopes constant value. We understood the application of TEFL's extrapolation in Evans diagram, which is used to study mixed electrode system. One example we saw showed us why zinc is nobler than iron using Evans diagram. And then in the case of galvanization, where zinc is in contact with iron, we saw how it corrodes faster than iron and how it gives galvanization protection to iron. We understood the final application of corrosion kinetics for calculating corrosion rate, which is based on Faraday's law. And now, with understanding corrosion chemistry, we talked about ways to control corrosion by dividing them into three categories: cathodic process control methods, anodic process control method, and metallurgical control methods. And finally, to end the discussion on corrosion, we talked about different in situ corrosion monitoring techniques. So I hope this much is clear to everyone. Okay. Now the final part of this course is about special purpose concreting. Now, till date, we have talked about conventional concrete, its mechanical properties, and its durability properties. But often, based on application demand, we may need to prepare a specific composition of concrete which cannot be prepared by common practices. Okay, so in terms of application demand, it is not just about the strength, but it is about meeting the required project demand, whether that's a lightweight construction or extreme durability or thermal insulation or even aesthetic requirements. Okay, and for all these types of special demand for specific purposes, we all the types of concrete, they come under the category of special purpose concrete. Okay, now how are special purpose concrete made? Okay, so these concrete are made by adding specific chemicals or admixtures, or by modifying the composition of concrete in a specific manner, like using chemical admixtures, superplasticizer and retarders, using supplementary cementitious materials like silica fume fly ash and GBFS, customizing the aggregates like either using lightweight aggregate or heavy aggregate or reactive aggregate, or by modifying the mixture design by controlling the water to cement ratio or setting time, or by modifying the curing technique for a specific purpose. Okay, so in this way we can achieve special purpose concrete. So this table just gives an overview of some of the common categories of special purpose concrete, how they are described and what are their key features. Okay, so there is high strength concrete, there is high performance concrete, lightweight concrete, self compacting concrete, air entrained concrete, fiber reinforced concrete, roller compacted concrete, pre stressed concrete, and reactive powder concrete. Okay, so at the end of today's session, you can revisit this table again. Okay, as it will provide you an entire summary of whatever we are discussing today. Okay, so most of these listed types we will be discussing today. Okay, so now let's start with a quick overview of some of these special purpose concretes, and we'll start with high strength concrete. Okay, so high strength concrete is defined as a concrete having compressive strength greater than 55 MPa, and such concrete are commonly used in advanced structural applications like where strain demand is more than 60 to 100 MPa. Okay, some examples where such type of concrete can be used are high rise buildings or bridges which are under extreme exposure conditions. Okay, so basically when we use a high strength concrete, when normal concrete can't handle the structural load or the environmental degradation. Okay, so in such conditions we need to go for a high strength concrete. So this same provision of strength is already discussed in week 4 or week 5 content, where we saw this table 2 of IS 456. So you can see ordinary concrete we have nominal mixture design, standard concrete is up till M55 grade, for which we have used IS 10262 for design, and for high strength concrete that is above M55 grade, we told that for preparing such concrete we need to engineer the concrete on our own, or we need to use mixture designs from past literatures for from people who have already prepared. Okay, now there are four key features when we talk about high strength concrete. First is the pore refinement. Okay, so lower is the porosity, higher will be the strength. Then second is low water to cement ratio. So we know water to cement ratio and strength have a inverse relationship. So lower water cement ratio again means higher strength. Then use of high range water reducing admixtures, because yes, I just saw the disconnection. I guess it interrupted just right now. I'll just change my connection setting so that it doesn't occur again. Just give me a second. Yes, now connection will be stable. Okay, so as I was saying, there are four key features of high strength concreting. First is pore refinement. Okay, lower is the porosity, higher is the strength. Second is the lower W by C ratio. Okay, so as we reduce the water to cement ratio, again strength increases. Third is the use of high range water reducing admixtures. Okay, because using high range water reducing admixture, they decrease the water demand for achieving a particular workability, and thus they help us to increase the strength. And fourth is optimizing the aggregate skeleton packing, because it ensures that there are minimum voids, so a lower amount of water demand will achieve certain workability that we require from concrete. So these are four key features that play a major role in developing a high strength concrete. Now, compared to conventional concrete, which has typically four component, a high strength concrete has five component system. Okay, which is key for achieving high performance and high strength. Okay, there is aggregates. So generally, aggregates are of smaller maximum size, usually 10 mm or maybe up till 20 mm. And using a smaller maximum aggregate size helps us to achieve better packing and lower porosity. And apart from size, high quality and well graded aggregates are also important because it improves the packing efficiency. Then cement. Generally, for high strength concrete, we use high early strength cement like type 3 cement of ASTM grade, or blended cement where silica fume or GGBFS or fly ashes are added. Okay, so cement content is usually high, 400 to 600 kg per meter cube to boost strength. But one problem that comes with using high early strength cement or high dosage of cement is the heat of hydration and shrinkage issues. So generally when we talk about high strength concrete, these two are some major issues with the concrete. Then water, So water must be very low. So generally water to cement ratio is kept between 0.25 to 0.35, because as we lower the water to cement ratio, we get a denser microstructure with lower porosity, which increases the strength and as well as durability. Then mineral admixture use is a must when we talk about high strength concrete. So silica fume is like mandatory, or it is very important to use where if you want to achieve a high strength concrete, because extremely fine pozzolana materials like silica fume, they improve the microstructure, they reduce the porosity, and they increase the strength as well as the durability. So generally 8% replacement of silica fume, of OPC by silica fume, and keeping a binder dosage of 450 kg per meter cube can help you to achieve a high strength concrete with a W by C ratio of 0.32 to 0.33. Okay, so this 8% addition of silica fume becomes very important because it helps us to replace, limit the OPC content also, and it helps us to achieve a high strength also, because if we'll use a very high cement content, then shrinkage issues will also come. So by reducing the cement content and adding silica fume, it helps us to negate these issues of hydration, heat of hydration, and shrinkage. Then chemical admixture are also essential to maintain workability at such low W by C ratio. So generally 1 to 2% by weight of cementitious material we add as SP dosage for a high strength concrete depending upon the workability demand. It helps us to produce a flowable, cohesive, and dense mix. Okay, without adding additional water. Now, often high strength concrete is seen as a with a myth that strength is all about cement paste composition, but in reality, it is not just about the paste composition, but it is also about the aggregate quality. Okay, so if you see this stress versus strain profile for a normal concrete. Okay, so we have this stress versus strain profile for aggregate. This is cement paste, and for concrete that is prepared by the combination of aggregate and cement paste, the stress versus strain profile lies somewhere in between. Okay, so we can understand that aggregate what is making the concrete superior in stress. Okay, cement paste is the weaker part when we talk about a concrete system. But now in high strength concrete, what happens? The cement paste quality has improved. Okay, so the stress versus strain behavior of aggregate, concrete, and cement paste, they lie at a very close interval. Okay, so but here, if we improve the aggregate quality further, then we can improve the quality of concrete also further. Okay, we can enhance the strength of concrete further. So that's why it is not just about the paste composition, but it is also about the aggregate quality. And if we compare the stress versus strain behavior of a conventional concrete and a high strength concrete, it shows higher capability to withstand stress. So you can see it has a higher strength stress bearing capability, but the strain at failure is much lower. Okay, if you see, failure has occurred at this much amount of strain compared to a normal concrete which is failing at this much strain. Okay, so strain at failure is much lower because of the brittleness that is imparted by the stiff aggregate and dense cement paste assembly. Okay, so as we increase the strength of concrete, the concrete becomes more brittle, so the strain at failure generally reduces. Okay, but although stress is increasing, but the strain is reducing. Now, how a high strength concrete performs for different properties apart from strength. So, this table shows uh, concrete with different W by C ratio, okay, from 0.26 to 0.75, and how they are performing for different durability properties. Okay, so just give me a second. So this 0.26 and 0.28 the based W by C ratio based concrete is the category for a high strength concrete, while these other W by C ratios from zero point 0.4 to 0.75, these are generally for conventional concrete. So you can see RCPT value, which is a judgment for durability against chloride ingress. It is much lower for a high strength concrete compared to a normal conventional concrete. Then at 90 days ponding, if we do chloride, if we estimate chloride concentration at a particular depth, say at 15 mm or 25 mm, we can see that chloride concentration is very small compared to what we found in a conventional concrete. Similar is the case with permeability. So you can see air permeability is much smaller value compared to conventional concrete in high strength concrete. Porosity is also much smaller in the range of 8 to 9%, where in conventional concrete it ranges from 11 to 13%. And similar is the volume of permeable voids, which is in the range of 6 to 8% in the high strength concrete, and it varies from 11.4 to 14% in a conventional concrete. So, all in all, since high strength concrete has a denser microstructure, its pore refinement ability enhances both strength as well as durability performance. Additionally, if we talk about creep, so there will be lower creep in high strength concrete compared to normal strength concrete because of denser microstructure and lower W by C ratio. However, in shrinkage, autogeneous shrinkage is significant in a high strength concrete. Why? Because there is low W by C ratio and very high binder content. Okay, so this, due to high binder content, there is more formation of hydration products, and we know how autogeneous shrinkage is the natural shrinkage that is occurring when cement and water reacts to form a cement paste. Okay, so since this reaction is happening more in a high strength concrete, so autogeneous shrinkage is more in a high strength concrete. However, drying shrinkage may be lower than the normal strength concrete because we have lower water content. Okay, so there is lesser chances of water evaporation to occur, so drying shrinkage chances are lower. However, in terms of fire resistance, generally high strength concrete is less resistant to fire and more prone to spalling or surface delamination due to fire. Why? Because there is low permeability in high strength concrete. Okay, so if there is fire inside, so the steams, they won't be able to escape the concrete. Okay, they will be trapped inside. There will be more heat absorption by the concrete due to high density, and moisture won't have path to escape the concrete. So due to dense microstructure, generally only problem that a high strength concrete deals is the loss in the ability of fire resistance. Okay, apart from this, for almost all the durability properties, a high strength concrete performs better than a conventional concrete. Okay, so if now we talk about ultra high performance concrete, so in this there are three categories. Okay, over ages there were three types of ultra high performance concrete that were defined. So first is the micro defect free concrete, which is also known as MDF concrete. Okay, so first up, as a matter of fact, this micro defect free concrete was originated by these two scientists to study the role of defect in strength reduction, and this paved the way for modern ultra high performance concrete. So their understanding about how defects affect the strength give the idea of how we can prepare a ultra high performance concrete. Okay, so we will just have a quick glance of what a micro defect concrete is, its characteristics, and its composition. So, a micro defect free concrete is an ultra dense cementitious material which is engineered to eliminate all kinds of microstructural flaws like porosity and cracks. Okay, by eliminating these flaws, we enhance the mechanical performance and durability of concrete. So, what are the key characteristics of such concrete? It has ultra low porosity because of dense matrix. That has very high binder content, usually using fine silica fume and low water to cement ratio below 0.25, and it has optimized particle packing of both aggregate and binder system. Okay, so generally what all materials we use, so in binder system we use Portland cement and silica fume in the range of 10 to 15% replacement. We use super plasticizers to maintain workability at such lower W by C ratio. We use fine sand with very low or no coarse aggregates. So when we talk about aggregates, we are using just sand and not even 10 mm or 20 mm aggregates when we talk about micro defect free concrete. And generally polymers like acrylic, epoxy resins are also used to enhance workability and chemical resistance. Okay, to fill the remaining voids inside the concrete. Then the next one in ultra high performance concrete is densified with small particle concrete, which is also known as designated as DSP concrete. So it is again a high performance concrete which is designed by maximizing the particle packing density using very fine particle, which result in a highly compacted and low porosity microstructure. So we have extremely low water to cement binder ratio in the range of 0.18 to 0.25. We use very high binder content, cement plus silica fume. There is no coarse aggregate at all, so uses fine sand. Okay, so here we are using sand in the MDF concrete. Here we are using even finer version of sand, less than 600 micron. Okay, it has very low porosity which reduces the defects and the capillary pores, and the strength that we get from a DSP concrete is, it is usually in the range of 150 to 250 MPa. Okay, now to manufacture such concrete we need to use OPC, silica fume, fine quartz, super plasticizers, and sometimes we use fibers and polymers also to enhance the properties. And the last one in UHPC, ultra high performance concrete, is reactive powder concrete, which is also designated as RPC. Okay, so the main again, as a matter of fact, this RPC was developed in 1990s by the scientist. Okay, and it is a like a progress to what what was found in a DSP concrete. Okay, so this RPC concrete, it is currently considered as the fourth runner of UHPC. So the current practice of UHPC is dominated by this concept of reactive powder concrete. Okay, so how this is UHPC? So it is developed by optimizing the particle packing, removing coarse aggregate, and incorporating reactive powders, fibers, and superplasticizer to achieve extreme strength and durability. So there is no coarse aggregate at all, which gives ensures a very uniform microstructure with lesser voids. There is densified matrix, cement matrix, which minimizes the porosity and micro cracks. There is fiber reinforcement, so generally we add fibers in such concrete, which enable strain hardening and ductile failure. We ensure high packing density of all the fines as well as cement paste, so that we can have a zero defect inside concrete. And for such concrete we need OPC and silica fume with a water to cement ratio even lower. Okay, so we discussed in DSP concrete it is in the range of 1.18 to 0.25, but in a reactive powder concrete it comes down to even 0.15. Okay, we are using fine quartz sand and ground quartz powder, okay, as aggregates. Super plasticizers, again we use high strength, high range water reducing admixture. And in reactive powder concrete, steel and PFA fibers, they become mandatory. Okay, now since we have talked about all three types of EHPC, let's see how they compare against each other. So main concept for all is the same: to eliminate, to make concrete denser and eliminate defects from concrete. Now in MDF concrete, water to cement ratio is usually in the range of 0.25. In DSP it comes down to 0.18 to 0.25, and in RPC it is in the range of 0.15 to zero point 0.2. The aggregates used, generally we use fine aggregate in all the three systems. No coarse aggregates are used. In SCMs, silica fume is mandatory in all three systems. While in DSP we also use quartz powder. While in RPC we also use some other mineral additives than grounded quartz. Okay, fibers is optional in MDF and DSP concrete, but in RPC concrete it becomes essential. And in terms of strength, a MDF concrete can range in the strength of 100 to 150 MPa. A DSP concrete ranges in the range of 150 to 250 MPa, and a RPC concrete can go from 150 to even up to 800 MPa. Okay, so this is how progress was made in a UHPC system over time. Okay, now based on your understanding about all the things that we have talked right now about high strength concrete and ultra high performance concrete, just try to answer these questions. And in the meantime, if you have any doubt, you can ask. Okay, so first question says, which of the following is most likely reason for increased autogeneous shrinkage in high strength concrete and ultra high performance concrete? So you know what is autogeneous shrinkage? It is the shrinkage happening due to hydration reaction of cement and water. Can you tell me the answer? Yes, the correct answer is C. Since we are using a low water to cement ratio, we are increasing the kinetics of reaction. Okay, so since there is more cement content and lower water content, so what is happening? There is a lot of hydration reaction which is happening. A lot of cement paste is forming, and that is giving rise to autogeneous shrinkage. But at the same time, since we have low water to cement ratio, then we are also decreasing the risk of drying shrinkage, because there is less moisture available from concrete to evaporate and to cause cracking in the system. Okay. Question number two. What is the primary function of polypropylene fibers in UHPC or high strength concrete under fire condition? Okay. So suppose a high strength concrete or a ultra high performance concrete is subjected to fire, and if those concrete has polypropylene fibers, so these are like kind of plastic fibers. Okay, if they have fibers inside them, how fiber will function in these fire condition? Can you tell me the reason why it happens? How fibers are providing vapor release channel? Okay, so the correct answer is C. Now, what happens when a concrete is under fire? So, moisture inside the concrete, it turns into steam. Now, what happens to these polypropylene fiber? They have a really relatively low melting point, so they can melt at around 160 degrees Celsius. Okay, so under fire condition, they melt. Okay, and since they melt, they leave behind a channel where the vapor pressure can be released. Okay, so since they melt and they give path for vapors to move, they reduce the risk of explosive spalling of concrete that can happen due in a high strength concrete, and this may make them crucial for fire resistance feature in a high strength or a ultra high performance concrete. Okay, as these fibers they can melt. Okay, and when they melt, they provide path for the vapors to move and to steams to move, which reduces the risk of spalling. Question number 3. Which curing method is often recommended for achieving high strength concrete in a reactive powder concrete? Yes, the correct answer is B. Okay, so generally, when we talk about any type of high strength concrete, so steam curing becomes an important factor, because as we increase the curing temperature, it increases the kinetics of reaction also. So, as we increase the kinetics of reaction, the pozzolanic reaction and hydration reaction, they accelerate. Okay, so it helps us to enhance the mechanical properties and microstructure density of concrete. Okay, in case of ultra high performance concrete systems. Okay, so that's why steam curing becomes an important thing, because as we increase the temperature, we are increasing the kinetics of the reaction. Question number 4. What distinguishes a ultra high performance concrete from a high strength concrete in terms of a mechanical behavior? Can anyone tell me? So we have two types of concrete. A high strength concrete, suppose its strength is around 75 MPa, and I have a ultra high performance concrete whose strength is around 150 to 200 MPa. Okay, so the correct answer for question number 4 is D. So what happens when we talk about a high strength concrete and the ultra high performance concrete, especially ultra high performance concrete with fibers. Okay, so if you see the stress versus strain profile, okay, so in a high strength concrete, the profile is like this. Okay, but in the ultra high performance concrete, the profile it is like this. Okay, because of the addition of fibers, it shows strain hardening. Okay, behavior in tension, and this means that it can carry tensile load or compressive even after cracking, and it exhibits a ductile response instead of a brittle response that we get in a high strength concrete, because there is fibers. So fibers, they will provide some strain hardening and ductile tension response. Okay, question number 5. In a UHPC concrete mix, the absence of coarse aggregate primarily contributes to what? Others also, please try to attempt. Like, can anyone else tell me what is the answer for question number 5? The correct answer is C. Elimination of weaker interfacial transition zone. So since we are not using coarse aggregate, we avoid ITZ formation between a cement paste and aggregate. And we know ITZ is the weak point. Okay, so by eliminating coarse aggregate, we achieve a denser, more homogeneous microstructure, which helps us to achieve higher strength and durability. Question number 6. In UHPC, suppression of calcium hydroxide in a hydrated matrix is advantageous because, yes, the correct answer is C. So, what happens in calcium hydroxide? We know it is relatively soluble and it is vulnerable to chemical attacks like carbonation or sulfate attack, or we have seen how in carbonation calcium hydroxide becomes vulnerable, or in sulfate attack also we saw calcium hydroxide is the first source where which leads to formation of CaSO4. Okay, so calcium hydroxide, we know if it is present in the pore solution, it makes concrete vulnerable. So in ultra high performance concrete, we use pozzolanic materials like silica fume, which shows secondary cementitious reaction where there they consume calcium hydroxide. Okay, so they suppress calcium hydroxide, and this contributes to a denser and more durable matrix with weaker zones. Zones means the presence of calcium hydroxide. Okay, so that is what we are minimizing in the ultra high performance concrete by suppressing calcium hydroxide. Okay, I hope the concept of high strength concrete and ultra high performance concrete is clear to everyone. If still you have any doubt, just post in the chat box your queries, or you can unmute and speak also. We can discuss the part again. Now, next up in the category of special purpose concrete is self compacting concrete. So, as the name suggests, self-compacting concrete, or also known as self-consolidating concrete, is a highly flowable, non-segregating concrete that can spread into place and fill the formwork completely under its own weight without the need of mechanical vibration. So such concretes are basically, when we pour such concrete in the formwork, they flow on their own. So we don't need to provide any kind of external vibration for compacting such concrete. Okay, so this concrete was developed in Japan in late 1980s to address labor shortage and durability concerns in concrete structure. Durability concern, how it can occur? Because if we are not providing proper compaction, there will be honeycombings and voids in the concrete. So to avoid such durability concern and to address labor shortages, self-compacting concrete was designed. Okay, especially in case of congested reinforcement area where concrete flow may not be proper. Okay, so what are the key characteristics of self-compacting concrete that makes it so special? Okay, so it has high flowability, where it can easily flow through formwork and around obstacles like rebar. So if we have rebars, caged structure of rebar. So in such cage structure, maybe a normal concrete which has a higher aggregate size, it may not be able to flow properly without proper vibration, but a self-compacting concrete will flow easily through the obstacles. Okay, and it will easily flow through the formwork. So the slump value of such concrete is typically very high. It is in the range of 650 to 800 mm, which is much higher than the conventional concrete. So for a conventional concrete, we generally have 150 to 200 mm slump. Okay, it has passing ability. It can pass through dense reinforcement caging without blocking, and it is achieved. How we achieve such passing ability? By using admixtures and optimized aggregate grading. Segregation resistance. So even though it has such a high slump value, it is cohesive enough to avoid separation of aggregates from cement place. So there is no bleeding. Generally, we have seen that if we add a very high SP dosage in normal concrete, we'll see that the cement paste and aggregate will separate. Okay, there will be segregation. But a self-compacting concrete is designed in such a way that even after having such high slump value, it won't show any separation of aggregate from cement paste, and it is self-leveling. So it naturally levels itself when it is poured. So we don't need any compaction force to be applied on the concrete. So in these image, you can see how self-compacted concrete appears. Okay, so we can easily see it is a highly flowable mixture from first image. There is nothing like segregation of bleeding which is happening, which is visible to us when it is getting poured. So you can see it is, we are pouring concrete at this point, and at this point also you can see cement paste and aggregate, they are cohesive. Okay, it is not like aggregates are separating and cement paste is bleeding anywhere. And in the second image we can see how it is freely flowing through the reinforcement caging. Okay, and it is self leveling itself, okay, under the action of gravity without the need of any compaction energy. Now, what are the key ingredients in a concrete mixture the designed for a self-compacting concrete? So, the use of super plasticizer is a must. It enhances the flow without adding water. Viscosity modifying admixture is needed to improve segregation resistance, especially in lean mixes. So, we know that when we increase the SP dosage, generally there are risk of segregation. To avoid that risk of segregation, we add viscosity modifying admixtures also. Then aggregate proportion, the size of coarse aggregate, it is generally limited within 10 mm or 20 mm, and its proportion is also lowered. So it is like only 28 to 35% of total concrete volume, and fine aggregate proportion is made higher. So it is like 45 to 50%, 55% of total aggregate volume. So we can keep like it will be around 60% of iron aggregate and 40% of coarse aggregate in total aggregate volume, instead of going with the 50-50 or 45-55 ratio. Then water to cement ratio is also kept usually high in zero point 0.8 to 1.1 range, to based on required strength and workability demand. Okay, and in this diagram you can see the entire flow chart. So in conventional, compared to conventional concrete, we are increasing the cement content, we are increasing the sand content, and we are reducing the coarse aggregate content. So in terms of cement, means cement plus mineral admixtures or all these chemical admixtures. Okay, so all those content, it is getting increased in a self consolidation or self compacting concrete. Now, how these things are engineered to make a self-compacting concrete. So this flowchart just shows you a short overview of the process. So first we start with packing density optimization of aggregates. Once we have optimized the packing density of aggregate, we choose the best proportion of cement and powder. Okay, which is determined using Plunke test for packing density. So this Plunke test is a test that is designed to optimize the packing density of binder system also. Okay, so first we have optimized the packing density of aggregate, then we optimize the packing density of binder system. Then we calculate how much paste volume is required based on void volume and required slump from concrete. Okay, once we calculate the paste volume, we decide the SP dosage, which is optimized using mini slump test. Okay, and once we have optimized the SP dosage, we use the viscosity modifying admixture. Okay, the that admixture dosage is again optimized using marble test. Okay, so it is a step by step process. First we are optimizing the aggregate packing density, then we are optimizing the binder packing density, then we are selecting the paste volume required, then we are optimizing the SP dosage, and then we optimize the viscosity modifying admixture dosage. And finally, if we talk about all these types of flowability or passing ability of cohesion property of a self-compacting concrete, on field, how will check whether a mixture is a self-compacting concrete? Okay, it has a good quality for a self-compacting concrete. So there are different tests. There is slump flow test, J-ring test, L-box test, and V-funnel test. So slump flow test, it tells us the flowability or spread diameter. J-ring test tells us the passing ability through rebar. L-box test again tells us the passing ability or blocking ratio. And V-funnel test tells us about the viscosity of the material. So you can see in U-box test, the figure 1 shows how the test is performed. So on the one side of the U-box, we have filled our concrete and this central gate is closed right now. Okay, now this central gate, it comprises of some obstacles. Okay, it will be like grid of different spacing as shown here. Okay, so when we raise this gate and we allow concrete to pass through this gate, so it will fill the other half of the u box. Okay, now based on the height of fill, we get an idea of the ability of concrete to flow. So if it is able to fill only a small portion on the other half, we say it has low flowability. If it is able to fill almost, it is level, concrete is level on both the side, then we have it has okay flowability. And again, if there is very small filling here, then we can say that there can be segregation issues also. Okay, if we see only cement paste is coming here and aggregates are collecting here, then we can get an idea of segregation issue, which uh, um, tells us that it is a too much flowable mix. Okay, where segregation is happening. Then there is slump flow test. Okay, so instead of measuring the drop in the height of concrete slump, we measure the spread of concrete. And from the spread of concrete, we record two diagonal values. Okay, and we calculate how much spread is there. Then there is V funnel test. So as per IS 456 criteria, for a SCC, for a concrete to satisfy SCC criteria, the slump flow should be in the range of 64 to 75 mm. So this is 640 to 750 mm. Okay, then V funnel test, it tells us the viscosity of a material. Okay, so we fill the concrete in this funnel, we close this from the bottom, and then when we open this, we record the time taken by the concrete to empty the funnel. Okay, so the criteria to satisfy SCC, it's like 10 plus minus 3 second, it should be able to empty the funnel. Then there is L box test, which is again similar to a U box test. Okay, so here we have filled the concrete. Here there is a gate which has 12 diameter rebars, okay, which will provide obstacle for concrete flow. Once we raise the gate, we'll see how much concrete is flowing on the up till this side. Okay, so based on the um, height of concrete on both the edges. Okay, so here is my, on this side I have my h1, okay, height of concrete here, and here I have h2. So based on this ratio of h2 to h1, we can get an idea of the flowability of concrete. So generally h2 by h1 should be at least 0.8, okay, if we want a scc concrete. Then, apart from these conventional testing, there is one more testing which is known as Sieves aggregation testing, and it is used to check the segregation or bleeding in a self-compacting concrete. So, how this test is performed, you can see from both figure and the flow chart. So, initially we fill the concrete in a bucket and allow it to settle for 15 minutes. Then, the top 2 liter of this concrete will pour on a sieve of opening 4.75 mm, and we place the pan at the bottom. Okay, and then we record the mass of pour, mass of concrete pouring upon the total mass. Okay, so the ratio, like how much concrete paste has escaped here, or what is the ratio between these two weight, it helps us to tell about the segregation that is happening in a self compacting concrete. Okay, so if this ratio is in the range of 5 to 15%, then we say it is satisfactory. If it is higher than 15%, then we say there is possible chances of segregation, and it is less than 5%, then we say that it has high resistance, it is not that much flowable. Okay, so this was all about self-compacting concrete. Okay, now just try to answer some questions regarding self-compacting concrete. And in the meantime, if you have any doubt, you can ask. So there is question number 7. In a self-compacting concrete mix, it shows a high T500 value. So how much time it took to spread to a 500 mm in slump. Okay, so it was showing a high T 500 time, means it was taking a lot of time to show a spread of 500 mm. So what is the probable issue in such concrete? Why it is showing such a high? Why it is taking more time to spread to a 500 mm slump? What can be the reason? Yes, the correct answer is C. So it has high viscosity and yield strength. So T500 this time is reflecting the flow rate of our self-compacting concrete. If the time is high, it means that our concrete has a slower flow rate, and that means that our concrete is sluggish due to viscosity. It has lower viscosity, so it is not able to flow freely. So due to high viscosity, it is not able to flow freely. Okay, so that means the concrete has high viscosity and yield stress, that is resisting concrete to spread. Question number 8. The potential of a for dynamic segregation in the self-compacting concrete during pumping of placement is most influenced by. So, what can be the reason for segregation in a self-compacting concrete during pumping or placement? Which parameter will define the segregation in self-compacting concrete? So, question number 8, the correct answer is C. Okay. Why? Because viscosity is the parameter which defines the segregation ability of a concrete. Viscosity means how how viscous is the flow of a concrete. Okay, if a concrete has higher plastic viscosity, it means that the concrete is not easy to flow. So such concrete, it means that the cement paste won't separate from aggregate easily. Okay, the entire cement paste and aggregate combination will flow together. So higher plastic viscosity, it helps us to resist segregation during a movement or flow. Okay, so when we talk about a self-compacting concrete, we are optimizing the viscosity also, and we are optimizing the flowing ability also. Yield stress, it just defines the initial stress required to make a concrete flow, and for self-compacting concrete, the yield stress value is almost negligible. Okay, it is the viscosity that will define the segregation once the concrete has started flowing. Question number 9. A compacting concrete mix shows excellent flow. Okay, slump was around 760 mm, but it failed J box or L box or J ring text. Okay, so it was showing flow, but the J box or L box or J ring test, it failed those tests. So what is the most possible indication of such concrete? What is the issue with the concrete? The correct answer is B. Okay, so since the slump value is around 760 mm, it has adequate flowability. However, since it is failing L box or J ring test, it means that the concrete has insufficient segregation resistance. The concrete is able to flow, but it is not able to navigate through obstructions easily. It means that it is too segregated, or it has coarse aggregate in it. Okay, which is making it not pass through obstacles easily. Okay, try to answer these three more questions regarding self-compacting concrete. Okay, so through questions you will be able to understand the concepts more easily. Okay, and these are like some of very standard questions which can be asked in exams also. So compared to conventional concrete, a self-compacting concrete generally shows what properties? Can anyone tell me the answer for question number 10? Yes, the correct answer is B. Why? Because we have a higher content of paste, okay, in a self-compacting concrete. Okay, there is higher paste volume, there is higher water content, so there is higher chance of shrinkage issues in a self-compacting concrete compared to a conventional concrete. Question number 11. Which of the following characteristics of a self-compacting concrete allows it to achieve higher durability despite its high flowability? So, though we are talking about high flowability, such a high water to binder ratio, why self-compacting concrete also achieves higher durability? Yes, the correct answer is B. Better particle packing and densification. So what happens in a self-compacting concrete? We are not using coarse aggregates. Okay, we are using fine aggregate, and we are optimizing the particle packing also. So due to optimized particle packing and a dense microstructure, we are able to achieve high durability despite having such high flowability in concrete. Okay. Question number 12. The modulus of elasticity of cell compacting concrete compared to a conventional concrete is typically higher or lower? Can anyone tell me whether the self-compacting concrete will have higher MOE or lower MOE? Okay, yes, the correct answer is D. Okay, since we are not using coarse aggregate, and we know that aggregates are the reason which which contributes primarily to a higher stress in concrete. So since we are not using aggregates much and we are increasing the cement paste content, so what will happen? This stress versus strain profile, it will shift downwards towards the cement paste curve, and thus a self-compacting concrete will have a lower MOE compared to a conventional concrete where there is higher proportion of aggregates. Okay, now the next topic that we are discussing is fiber reinforced concrete. Okay, so now, if we look at how the use of fiber came into existence in concrete, so this concept of fiber, the concept of mixing mud and straw date back to this Egyptian and Mesopolitan era, okay, where fibers were used to prevent cracking and shrinkage during drying. Okay, so it is long back when people started mixing straw in mud to prevent cracking in structures. Okay, so from that time this concept grew, okay, of fiber reinforced concrete. This ancient knowledge, it led the formation of modern fiber reinforced concrete, where distinct fibers are added to concrete to improve performance, especially tensile performance, toughness, and crack resistance. Okay, now there are different types of fibers that are available in market, so depending upon the application need, we can use specific type of fiber. Okay, there is steel fiber which enhances the toughness and impact resistance. There is glass fiber which is used for lightweight application. There is synthetic fiber like polypropylene or nylon fiber which reduces plastic shrinkage, and there is natural fiber like jute fibers which are low cost and sustainable solutions. Now, what is the role of fibers in our fiber reinforced concrete? Okay, so fibers that are used in fiber reinforced concrete, they are short, randomly oriented, and uniformly distributed. Okay, so we add fibers as an admixture in concrete. Okay, so they are very short fibers. Okay, and they are oriented randomly inside the concrete, and they are distributed uniformly because we are adding them at the time of mixing. And what they do, they arrest the crack, they bridge the microstructure, and they improve the ductility of concrete. So the same we can understand from the figure also. Okay, where we can see a concrete. Okay, this is a concrete cube which is broken from the middle, and in the failure zone we can see how fiber is acting as a holder thing, kind of thing. It is resisting concrete from breaking apart. Okay, so this fiber is going from this end to this end, and it is not allowing concrete to completely break apart. It is bridging the cracks. Okay, it is arresting the cracks inside the concrete, and it is increasing the strength of concrete. Now, it is not just about the fiber material, but the orientation of fiber is also important. Okay, there are vertical fibers. If all the fibers are aligned vertically, then only the vertical component of fiber will contribute to load resistance. Then horizontal fiber, again, only the horizontal fiber component of fiber will contribute to that direction. Okay, and there is random fiber. So in real reinforced concrete, fiber reinforced concrete, the fibers are randomly oriented in 3D, so that we can have an average effectiveness along all the direction. Okay, because the load can come from horizontal direction also and from vertical direction also. So having a random orientation of fiber gives us that edge, that effectiveness is there along all the possible angles of loading. Now, if we see the stress versus strain relationship of how these fiber reinforced concrete look under loading, So compared to a conventional concrete where we have two more extra cases, a fiber reinforced concrete with low volume of fiber and a fiber reinforced concrete with high volume fiber. So first is the increment of ultimate load. So compared to a conventional concrete, we can see that in fiber reinforced concrete, it has higher ultimate load, and that especially in case of high fiber volume. Okay, we can see that in a high fiber volume, the stress, ultimate stress is much higher than what we get in a plain concrete. And second is the behavior post peak. So conventional concrete, it fails suddenly. Okay, while a fiber reinforced concrete, it shows strained softening behavior. Okay, and this increases the net strain taken by concrete before failure because fiber are bridging the cracks. Okay, they are not allowing concrete to fail easily. So that's why concrete shows some strained softening behavior. And as this failure is getting delayed, we are also increasing the toughness of concrete. So toughness is nothing but the area enclosed by the stress versus strain profile. So as we are delaying the failure, we are increasing the toughness of concrete also. The same thing is written in these 3 points also. The fiber addition, it shows post cracking ductile behavior. Fiber bridges the cracks, which shows strain hardening or strain softening depending upon the type of fiber, and it really increases the energy absorption capacity. That is the toughness of concrete also. Now it is again not just about the volume of fiber, like high volume or low volume. The behavior of a fiber reinforced concrete also depends upon the shape, size, and the property of fiber. So straight fiber, they are easy to mix, but they are difficult to bond. Okay, there is crimped and wavy fiber which better grips with concrete, and there are twisted fiber which enhances the friction and pull resistance. Okay, so instead of straight fiber, if you have a crimped fiber or a twisted fiber, they can perform better. Okay, then there is size of fiber, subtract ratio, length to diameter ratio is a key when we talk about fibers. Okay, if I have a high abstract ratio, they are able to bridge crack better, but however too high can reduce workability also. Okay, so we need to maintain that aspect ratio in a certain range. Short fibers, they are generally good for shrinkage resistance. However, long fibers, they are good for load bearing and structural application. So depending upon the type of application, we can use a short fiber or a long fiber. Then effective material property. So tensile strength, a higher strength fiber like steel fiber or glass fiber, it performs better and for load transfer. Elastic modulus, if we have high elastic modulus, it controls the cracks effectively. Or if you have a low elastic modulus of fiber, like for polypropylene fiber or natural fiber, they are good for plastic shrinkage. Okay, and how the fibers bond with matrix, that is cement paste. Okay, that is also important. So if I have a rough structure texture of fiber, or we have a crimped fiber, or we have certain silica coated fiber, they bond more better with cement paste around them. Okay, which increases their efficiency. And finally, how a fiber reinforced concrete behaves at different stages post concreting. So fibers, they generally reduce the workability because they are making concrete stiff. Okay, if we add high volume of fiber, so to compensate against this, we use super plasticizers. Then strength, a fiber reinforced concrete may or may not increase the compressive strength. Okay, depends upon the volume of fiber. However, tensile strength and flexural strength are significantly improved. Why? Because fibers are bridging the cracks. Okay, so the crack resistance increases even under cyclic or impact loading. Then durability property. So fiber improve the resistance to freeze and thaw action. It improves the resistance against impact and abrasion, and it improves the resistance against plastic shrinkage also. Okay, so in all these properties, fibers can give a positive impact. However, if we are using steel fibers, they may corrode also if they are exposed to marine exposure. Okay, so in such cases where we are near shoreline or where risk of corrosion is high, instead of going for steel fiber, it is better to go with the synthetic or natural fiber which are corrosion resistant. Now, often when we use fiber in concrete, we are confused in two terminologies. There is FRC and there is FRP. So FRC is fiber reinforced concrete. Okay, in this fibers we are adding as an admixture inside concrete. Okay, while FRP is fiber reinforced polymer concrete, where we are applying a fiber wrap in a hardened concrete outside concrete. Okay, so this FRC, it is used for enhancing the strength of concrete, whereas FRP is also used for enhancing the strength, but in terms of a retrofitting measure. So original concrete has M40 strength only, but using FRP wrapping, we are increasing the M40 grade to M55 grade after we have casted the concrete. While in FRC, we are increasing the original strength of concrete as it is. Okay, so FRC, it enhances the intrinsic property of a concrete mixture, while FRP, it is a reinforcing material usually used externally or internally. So you can see here in the first image, we have fibers that are inside concrete which are bridging the crack. Okay, while in the second image, you can see this black wrapping. So these are CFRP, carbon fiber reinforced polymer. Okay, so we are wrapping these concrete on a concrete column. And what is this wrapping do? It is providing confinement to concrete, and it is enhancing the strength of concrete, the axial strength carrying capacity of concrete. Okay, so that is the difference between a FRC and a FRP. Okay, this was all about fiber reinforced concrete. Any doubt in this section? If no doubts, we'll move ahead. So after a fiber reinforced concrete, we have roller compacted concrete. Okay, so roller compacted concrete, it is generally opposite of a self-compacting concrete. So this concrete is a very dry concrete mix which has zero slump. Okay, and it is compacted using roller. So in the self-compacting concrete, we saw the compaction happens naturally. We don't need to apply any compaction force. However, in roller compacting concrete, the concrete is very dry. It has no slump, and we compact such concrete using rollers. Okay, so this concrete uses the same ingredients that are used in conventional concrete, but it with a very low W by C ratio and very high amount of fine aggregate to maintain workability in a dry mix. Okay, so we have cement which act as a binder, we have water which is very limited, just enough for hydration so that there is no slump. Aggregates are again coarse and fine aggregates, and admixture, generally we don't use any chemical admixtures like SP. However, mineral admixtures like fly ash, slag, or some amount of water reduce normal range water reducers can be used to enhance performance. And since this concrete has lower water content, it has almost zero slump, meaning that it doesn't flow like a normal concrete. It is like a damp soil. What are the key features of such concrete? It has dry consistency, zero slump. Okay, so it compacts by vibratory roller. It has fast placement and minimum formwork need. Okay, there is high strength and durability in such concrete because water content is very low, water to cement ratio is smaller, and it has low cost because we are using less cement and more aggregate in such concrete. Okay, so if you see how roller compacted concrete looks like, so as you can see in the first image here, the concrete is dry enough, okay, to avoid any sinking, okay, under the action of roller equipment, but you can see it is wet enough to provide sufficient distribution of binder motor in concrete, okay, during mixing and during vibration. The same we can understand from the second image also, where again concrete seems to be dry enough, but it has still enough wetness so that it will undergo proper compaction. Okay, in the third and the fourth image, you can see the application of a roller compacted concrete in building dams. Okay, so here they have poured a roller compacted concrete, and now they are compacting that concrete using rollers. And for concrete pavements also, generally roller compacted concretes are used. Okay, so these two are like most common application of a roller compacted concrete in mass construction activities. Now, based on your understanding about fiber reinforced concrete and roller compacted concrete, just answer these few questions. So, question number 13 says, which of the following best explains the high aspect ratio fibers in FRC and why they may reduce overall concrete performance? So if we use a very high aspect ratio, the length to diameter ratio of fibers in the FRC, how they can reduce the overall concrete performance? Can anyone tell me? Yes, the correct answer is D. Okay. So what happens? High aspect ratio fibers which are long and thin, they are prone to clumping. Okay, so they will form a clump like they will entangle with each other and they will form a ball. Okay, they will entangle with each other and they will form like so this is like fibers, they will clump together. Okay, and they will form a fiber balling. Okay, this is known as fiber balling. So they won't be able to disperse properly, and this will directly affect the workability, and it will make concrete and it will make the concrete matrix non-uniform. Okay, so this is known as fiber balling. Okay, which happens in high aspect ratio fiber which are not able to disperse properly. Question number 14. The modulus of elasticity of fibers in a FRC affects what? Yes, the correct answer is C. So when we talk about elasticity modulus of fiber, a higher elasticity modulus means that fiber can resist more deformation. So it can carry more load even after cracking, and if it is able to carry more load after cracking, it can bridge crack and it can control the crack width. Okay, especially under tensile or flexural stresses. Okay, so that's why modulus of elasticity contributes into the cracking and load transfer efficiency post cracking of concrete. Question number 15. What happens when fiber content in FRP exceeds the optimum value? So suppose optimum volume was 2%, now I'm adding 3% and I'm not adjusting anything else in the mixture. So what will happen? Yes, the correct answer is B. So what happens if we are adding excessive fibers in concrete? So they will, without modifying the concrete mix, like without adding more super plasticizer, they reduce workability and they increase the mixing difficulty because fibers are stiff. They impart stiffness to concrete. Okay, so if we add more fiber than required, they won't spread properly first thing, and they will make the concrete stiff, so they will reduce the workability. Okay, so, and there is poor fiber dispersion because they will undergo balling. Fiber balling will increase as we increase the proportion of fiber in concrete. Question number 16. Which of the following is the primary reason why roller compacted concrete is not suitable for highly reinforced concrete structure? Highly reinforced concrete means when there is high percentage of steel reinforcement inside concrete. So for such concrete, why we don't prefer to use a roller compacted concrete? Yes, the correct answer is C. Because we know in roller compacted concrete it has zero slump, zero workability. Okay, it is very stiff. Now, when we talk about a reinforced concrete which has a dense reinforcement caging, so if the concrete is very stiff, it won't be able to flow through the spaces between the reinforcement. Okay, so that's why a roller compacted concrete it is not ideal for a reinforced concrete structure. Now, in a roller compacted concrete dam construction, which what is the most crucial factor to ensure interlayer bonding? Like to ensure that all the layers of the concrete that we are placing and that we are compacting using lower rollers, what is the factor which is important to ensure that the layers are bonding properly? Yes, the correct answer is A for 17. Okay, the moisture content at the time of placement. So, for good bonding between successive layers of a roller compacted concrete, the moisture content and the surface condition of the previously placed layer is very important. If a concrete surface is dry and it has become stiff, then the layer that will place above it won't bond properly. There will be cold joint at the interface. Okay, so that's why moisture content becomes important. Question number 18. Main reason fly ash is often used in roller compacted concrete. So, why generally people add fly ash in roller compacted concrete? Okay, you have already given the answer for question number 18. D. Yes, the correct answer is D. Why? Because when we talk about this RCC, RCC is mainly used in mass concretes like for dams or for pavements. Okay, and in such concrete, in mass concrete, the risk of the heat of hydration is high. The drying shrinkage risk is high. Okay, so what happens when we add fly ash? It reduces the risk of heat of hydration, and also to lower the cement content, we use fly ash, which makes the concrete mix more economical. Okay. Now, after roller compacted concrete, we have polymer composite concrete. Okay, so these are advanced material in which we use polymers. We combine polymer with traditional concreting material. So, what are polymers? So, polymers are generally composite which has properties like high strength, rapid curing, and excellent chemical resistance and reduced permeability. Okay, there are three types of polymer concrete composites that are present. There is polymer concrete where instead of cement used as a binder, we have polymer as binder. Then there is polymer cement concrete where both cement and polymer are binder. And then there is polymer impregnated concrete where polymer is impregnated into hardened concrete. Now, what do you mean by polymer? So, polymer is generally resin plus hardener system. Okay, so these are like epoxy based material which are added, which have high strength. Okay, which are added in concrete. Now, how these three types of polymer composite concrete differ from each other? So, if we look at the composition, okay, in polymer cement concrete, we have cement plus water plus polymer plus aggregate, which is making a polymer cement concrete. In polymer concrete, we have aggregates plus polymer resin, which is making the hardened concrete. So we don't have cement and water in such concrete. And in polymer impregnated concrete, we have already a hardened concrete system. Okay, and in the pores that are present in the hardened concrete system, we are introducing this low viscosity polymer. Okay, so this polymer, it when it goes inside the pores and it undergoes polymerization via heat or via radiation. Okay, and it blocks the pores and it hardens the concrete. Then binder, so in polymer cement concrete, both cement and polymer are binder. While in polymer concrete, there is 100% polymer and no cement. So in PCC, polymer act as an inert filler. Okay, it reduces the porosity and increases the strength, and it enhances the adhesion and water resistance ability also because polymer are hydrophobic in nature. And in polymer concrete, polymer it has high strength and chemical resistance, and it sets quickly even at low temperature. Okay, that are the key properties of polymer concrete. While in PIC, the polymer they are filling the pores. Okay, so they are making already hardened concrete much more stronger and less permeable. Now, PCC it is generally used for overlays or patch repairs, while PC concrete are generally used for covering manholes or industrial flooring, like at the roof of a structure, we use PC concrete for flooring purpose so that water doesn't permeate inside. And PIC, it is generally used for retrofitting work. So if we see cracking in a bridge deck or in a parking lot or in pavements, so we impregnate polymer injection. We give impregnate the concrete crack through polymer injection to fill the voids and to reduce the transport of water or leakage in those structure. Now the next two concrete, special concrete that we are discussing, that will be discussing, will be related to the density of concrete. So first we have heavy density concrete. Okay, so heavy density concrete is a type of concrete which are made with heavy weight aggregates instead of normal aggregates like gravel and sand. And this is done to increase the density of concrete above, typically above 300 kilonewton per meter cube. Okay, standard concrete has a density of around 2400 kg per meter cube. Okay, what are the main components of heavy density concrete? Cement is there, water is there, and we have heavy weight aggregates like barite, magnetite, hematite, or scrap irons. Okay, so these heavy aggregates are used instead of normal aggregates, and their key properties is like their density. For heavy density concrete can go up till 6000 kg per meter cube. It has excellent radiation shielding because of high density. It has high compressive strength because we know strength is a factor of both cement paste and aggregate. So if we are increasing the density of aggregate, we are increasing the stress bearing capacity of aggregate also. So overall we are increasing the strength of concrete also, which lies between cement paste and aggregate. And such concrete is slightly difficult to handle because of their heavy weight. Okay, now where is such concrete used? So it is used generally for radiation shielding in nuclear plants or in hospitals, because high density of concrete because of the high density of concrete, it absorbs radiation. So you can see there is high radiation on this side. This object is my high density concrete, and only a small radiation was able to penetrate. The remaining got attenuated because of high density of concrete. Heavy aggregates, they absorbs the radiation and they prevent penetration of radiation through the structure. Then in ballastic application, okay, we used heavyweight aggregate concrete to increase the absorption capacity against any kind of impact. Okay, for counterweights in bridges or in elevators or in crane, we use heavyweight concrete. In military applications like bunkers or blast protection, generally heavyweight aggregates are used because heavy density concrete are used because of their high vibration resistance. Okay, they can absorb more energy, so that's why they are used in military applications also for making bunkers or blast protection structures. Then opposite to heavy concrete is lightweight concrete or low density concrete. So these concrete are designed to reduce the dead load or to improve the insulation ability of material with lower density. So their density is in the range of 300 to 2000 kg per meter cube, which is lower than conventional concrete density. Okay. Now a concrete can be made lightweight using different in several means, by removing aggregates from the system like pervious concrete, by using lightweight materials in concrete like lightweight aggregate, or by increasing the air void content in concrete like autoclave concrete or a foam concrete. So the one of the main feature that we talk about a lightweight concrete, is it thermal insulation ability. Okay, as you can see in the in the figure also, as we increase the porosity of concrete, the lighter the concrete will become, and the thermal conductivity of concrete also decreases proportionally. Okay, so it is making concrete thermally insulator. It is acting like an insulator. Now let's have a quick recap of each of the type of lightweight concrete. Okay, so we have lightweight aggregate concrete, where instead of normal aggregate we use lightweight aggregates like clay, shell, pumice, or perlite. So the aggregate density is lower. So as we decrease the density of aggregate, we are decreasing the density of concrete also. Now where are such concrete used? They are used for structural application like in high rise buildings. So when we talk about high rise building, at higher floors we generally use lightweight aggregate concrete to reduce the dead load on the lower floors. Okay, then we can also make aggregates from fly ash. Okay, fly ash based aggregates are also made, which are lightweight. Okay, and this process is known as palletization. Okay, so in the first image you can see concrete made with lightweight aggregate. Okay, this black circular aggregates that you see, these are fly ash based aggregate. And in the second image you can see how these sintered circular lightweight aggregate they look like. And this third image shows the palletization instrument where we prepare a lightweight aggregate using fly ash. So basically what we do, we pour fly ash in this tray, and we rotate this into instrument at a particular angle and at a particular rpm, and we slowly add water to the fly ash. So what water does, it agglomerates fly ash particle into circular balls. Okay, once these circular balls are made, they are heated and they are dried to form the aggregates. Now once these aggregates are made, we make low density concrete out of them. Then there is foam concrete, okay, where we, instead of cement, water, fine aggregate, and instead of just cement, water, and sand, we add a foaming agent also, okay, which creates air bubbles inside concrete and it reduces the density of concrete. So their strength is only low to moderate, so they are generally used for non-structural application. Okay, so these are kind of foam concrete. Then there is autoclaved aerated concrete, okay, which are again a precast factory made lightweight concrete. So in this, what we do, we use aluminum powder. Okay, in this powder, and when we make a concrete with aluminum powder and we cure it under steam, so what happens? These aluminum powder, they create gas bubbles inside the concrete, and it reduces the density of concrete. So they are good for non-load bearing applications. Okay, in low rise building, or their strength is generally low. Okay, so like AC blocks, you will see they are very popular in modern construction. Okay, they have good insulation ability also, and they are used to make a lightweight structure. Okay, low rise building. Then the last type of lightweight concrete is pervious concrete. Okay, so it is not always lightweight, but like it is often included in unique structure. So in this, what we do, we make concrete without fine aggregates. Okay, so we have coarse aggregate, we have cement, we have water. So when we remove fine aggregates, so what is happening, we are increasing the porosity inside concrete. So density of such concrete, it is lower than conventional concrete, and its strength is also lower. And such concrete, they are used in pavements or parking lot or drainage management system, because they have high porosity, so they allow water to easily pass through them. So in flooding areas, you will find the application of pervious concrete. So both of these images that you see here, these are from my project work from IIT Indore only. So in the first image, you can see water permeating through a pervious concrete paver block. And in the second image, we made an attempt to make a brick that was prepared with a pervious concrete mixture. So you can see this mixture, it has high porosity, which is clearly visible. So there was no fine aggregate used to make such concrete. Now try to answer these three simple questions based on PIC and heavyweight concrete, density concrete. If you have any doubt in the section that we have discussed, you can ask. NPTEL exam question. The questions will come from the entire course discussion that we are doing. So whatever the professor is taught in the NPTEL sessions, and whatever I am covering in the live sessions, all these are the part of course only. We are not talking anything apart from course. So any topic that has been taught, it can come. Okay. Pattern, I guess generally it is objective paper only, or it can be subjective small questions. The questions that you see in assignments, the same type of questions can come. And marking and all, you need to ask the NPTEL team, what is, how much marks is there for those paper. Right now, just try to answer the questions quickly. So question number 19 says, which of the following best explains the improved mechanical property of a polymer cement concrete compared to a traditional concrete? Yes, the answer is C. So what is happening when we talk about polymer modified concrete? So polymer, it forms a film across the cement paste and it enhances the adhesion and the tensile strength and the durability property. So polymer, it is like, it is filling the voids that are present in the system. So it is bridging all the micro cracks, it is reducing porosity, and it is increasing the mechanical performance of concrete in general. Question number 20. In a polymer impregnated concrete, polymerization is commonly initiated using. So, what happens? We inject the polymer inside the concrete and then we need to polymerize the concrete such that the polymer, it expands and it fills the cracks. So, that expansion or increasing the activity of polymer, it is known as polymerization. Okay, linking of polymers together. Okay, so that they can fill the entire crack. Okay, so that polymerization, how we do that polymerization? Yes, the correct answer is A, using UV light or using heat. Okay, so what happens in a polymer modified concrete, we have a dry concrete, and in the cracks that are present in those concrete, we impregnate a liquid monomer. Okay, a liquid solution we impregnate. Now, to polymerize that monomer, we use UV lights or heat. Okay, so what these UV light or heat do, they cause monomer to harden, okay, into a polymer. And when monomers are like single units of a polymer, when they harden and then when they link with each other, they fill the concrete pores. Okay, and they increase the strength and the durability of concrete. Question number 21. Which nuclear shielding parameter is directly influenced by magnetite based heavy concrete? So when we talk about nuclear shielding, which parameter is influenced when we use heavyweight concrete? Yes, the correct answer is A. So we have seen that when we talk about heavyweight concrete, the heavyweight aggregates, they have ability to reduce the intensity of radiation passing through them. Okay, like magnetites, they absorb the radiation. Okay, so they have a high linear attenuation coefficient, like you saw in the image here. Okay, the radiation, they are getting attenuated due to high density of aggregates that we are using, so lower amount of radiation is passing through. Okay, so that is the attenuation factor that is enhanced when we talk about heavyweight concrete, and that contributes to nuclear shielding. Okay, now the final topic of this course, and in special concrete, it is related to sustainability and sustainable construction practices, and that is recycled aggregate concrete. Okay, so a recycled aggregate concrete is produced using recycled aggregate from construction and demolition waste such as crushed concrete, masonry, and bricks and asphalt in place of natural aggregates. So instead of using natural aggregate, what we do, the already existing building that are demolished, the aggregates from those building we use again. So that's why we say them as recycled aggregate concrete. And the main aim of this concrete is to reduce environmental impact, promote circular economy, and conserve natural resources. So instead of using natural aggregates, we are using recycled aggregates, and we are creating a circular economy. So we are constructing a building, and after demolition we are using the waste generated from building to again construct a building. So this is circular economy, and we are reducing the environmental impact also, so we are not depleting the natural resources. Okay, so the main component of a recycled aggregate concrete is cement, water, recycled coarse or fine aggregates that you can see here, and admixtures or performance enhancer as per the required durability, strength, or workability. Now, though these RCA they promote sustainable construction, there is a major problem when we talk about the integrity of concrete made with recycled aggregates. Okay, and that is the reason why recycled aggregate concrete have much smaller strength than a concrete made with natural aggregate. Okay, why this happens? This happens due to the presence of adhered mortar over the aggregates in the RCA. Okay, so if you see this aggregate image, which is taken from a construction and demolition waste, there is already aggregate and there is cement paste layering also, which is present over the aggregate. Okay, in this portion. Okay, so this is my aggregate where there is no cement paste above, and this is my aggregate surface where there is cement paste layering. Okay, there is mortar cover over the aggregate. Now, this cement paste has already hardened and it has adhered to the aggregate. So, what happens due to the presence of this adhered mortar over the aggregate, the bonding between the aggregate and the new paste. Okay, when we are again using this aggregate for one more construction, the fresh cement paste won't bond properly with the aggregate because of the presence of this adhered mortar, so that will make a weak ITZ. Okay, the ITZ between already existing mortar and new cement paste will be weaker compared to what it would have been between cement paste and aggregate. Okay, and this mortar, it is porous in nature also. Okay, so since it is porous in nature, it has high absorption, high water absorption, it has low specific gravity. So all these reasons they contribute to poor quality concreting. Now, to improve the quality of this recycled aggregate concrete, there are several treatment methods that are available. And these treatment methods, they are broadly classified into two categories. Either we need to eliminate the adhered mortar, or we need to improve the quality of adhered mortar. For eliminating, we can use physical treatments like thermal treatment. We can heat the aggregate, we can make the adhered mortar weak so that it will be removed. Mechanical treatment is like rubbing the aggregates to remove the adhered mortar, or using water soaking. So water soaking again can make the adhered mortar weak and so that it can be removed. Then this chemical treatment like acid soaking or chemical mechanical treatment. So these techniques are also used to eliminate adhered mortar. Then for improving the quality of adhered mortar, we use polymeric treatment. So the same thing that we saw in polymer concrete, in adhered mortar also we dip those aggregates in polymer. So polymer, what they will do, they will penetrate through the pores that are present in the adhered mortar and they will densify the pores. Okay, so that will reduce the water absorption and that will increase the specific gravity of aggregates. Then there is biodeposition technique that is used. There is incorporation of pozzolanic material or carbonation of adhered mortar. So these are some techniques that are used to improve the quality of adhered mortar. Now, one of these categories that I used in my undergrad was thermomechanical treatment of aggregates. So I can tell you how this treatment process works. So first, I have a mixed recycled aggregate. You can see there is aggregate of different size. There is brick and there is stone. So there are different types of impurities that are present in this aggregate. Okay, there are mixed recycled aggregate. So first this aggregate is heated at different temperatures. I heated the aggregates at different temperature. When we do heating, what happens? The adhered mortar layering, it becomes weak. Okay, now after making the layer weak, to remove the mortar, the heated aggregate was then given mechanical treatment using Los Angeles abrasion machine. So in this rotating drum, we loaded the aggregate and we added some steel balls and we allowed aggregates to rotate. So the aggregates then, when they will stuck each other, the mortar, it will weaken and it will remove. Okay, so once we have removed the mortar from aggregate, we'll sieve it and we'll get our coarse aggregates, and those aggregates we used for making concrete. So the treated aggregates, had a better strength compared to untreated aggregate, and they were close compared to natural aggregate. So at 700 degrees Celsius heating followed by mechanical abrasion, the aggregates that we got, they had almost comparable strength as natural aggregate. Okay, so in this way we can improve the quality of reinforced concrete aggregate also. Now try to answer these three simple questions regarding RAC. And in the meantime, if you have any doubt regarding reinforced concrete aggregates, you can ask. You can go through the lecture recording, okay? Because the explanation it will take time, and we don't have much time. Only 10 minutes is left. Or I will just give you a short overview. In RAC, what happens? We are getting aggregates from construction and demolition waste. Okay, so these aggregates they are not that good quality as natural aggregate because there is adhered mortar layering over the aggregate, and this adhered mortar it weakens the bond between the new cement paste and aggregate. Okay, so we get poor quality concrete when we use recycled aggregate. Now there are several ways in which we can improve the quality of recycled aggregates. So either by eliminating the mortar or by improving the quality of mortar that is there over the aggregate. Okay, so this table I showed for different ways, different technique methods that are available. And then finally we discussed one of the technique method where what we are doing, we are collecting aggregate, we are heating the aggregate. So heating will soften the adhered mortar, and then we are providing mechanical treatment, so we are rubbing the aggregates against each other, so that will remove the mortar. Once we remove the adhered mortar, the aggregate quality improves. So I found that at 700 degrees Celsius heating followed by mechanical abrasion, the quality of aggregate was close enough to natural aggregate in terms of compressive strength of concrete. Okay, so this is all we discussed in recycled concrete aggregate. So you can again revisit the session recording to listen in detail about this. Okay, question number 22. The correct answer is, can anyone tell me the correct answer of question number 22? Which property of recycled aggregate concrete is most likely influenced by the interfacial transition zone between old mortar and new paste? So the correct answer will be compressive strength. Because what happens, the ITZ is weaker between adhered mortar and new paste. Okay, so if ITZ is weaker, the compressive strength will be lower, and that is why we say quality concrete quality is poor when we use recycled aggregate. Question number 23. Which factor significantly influences the durability of RAC? Okay, for 23, the correct answer will be A, B, and C. Okay, so quality of parent concrete it defines the quality of adhered mortar over aggregate, and it defines the quality of aggregate also. Crushing process again defines whether we are cracking the aggregates or we are just removing the adhered mortar. Okay, so if we are crushing aggregates a lot, okay, then what we'll do, we'll weaken the aggregates also, where we'll crack the aggregates also, which can affect the durability of a recycled aggregate concrete. Then replacement percent is important. Generally at lower replacement percent, our concrete durability is higher compared to a higher replacement percent of normal aggregates with recycled aggregates. Okay, and type of curing won't affect much, okay, because curing in general influences all types of concrete and not just recycled aggregate concrete. Okay. Question number 24. Which property is most likely to be compromised when we use a lightweight aggregate concrete if the aggregates are not pre-saturated? So using recycled aggregates also we can make lightweight aggregate. Okay, lightweight aggregate concrete. What property will be compromised if we don't soak the aggregates initially? Yes, the correct answer is workability. Why? Because lightweight aggregates, they are highly porous, okay, and they absorb water from the mixture. So we know that water absorption and moisture absorption is very important factor when we do mixture design. So if we don't take into account the water absorption capacity of lightweight aggregates properly, so what they will do, they will consume water from the water that we added for reaction. So they will effectively reduce the water to cement ratio. They will make concrete dry and less workable. Okay. So this was all from today's session. We discussed about special purpose concrete. We had a brief overview. Then we discussed about high strength concrete and high performance concrete. We discussed about self compacting concrete and different testing methods used to validate a SCC mixture. We discussed about FRC, RCC, and polymer concrete composite, heavy concrete, lightweight concrete, and finally we discussed about recycled aggregate concretes. So this was all for the session. Thank you.